Hey guys, how's it going? My name is Remy, and this week I wanted to share with you a fun little puzzle program I found online. The goal is to program a robotic arm to move blocks of varying sizes from one side of the grid to the other over varying obstacles of varying sizes. So the problem was actually presented to me at my university back when I was studying during my first semester, and I found it fascinating at the time. I recently found it online in a GitHub account of somebody who I presume is a current student there. So I solved it, and I felt like it was a good idea to share it with you guys because it serves as a great intro to fundamental concepts such as the if statements and the loops. So basically, how the program works, the is is as follows. You have a robotic arm. Let's say the robotic arm is, so you have a grid. Let's first imagine a grid, right? The grid is 13 of height 13 by 10. So the grid is 13 by 10. So you have a robotic arm. It is right here and is in position 1. So this is the robotic arm. Let's call it R. On the other end, at the position 10, you have blocks of varying sizes. So you can have a block of size 3, a block of size 2, and 3 is the maximum, by the way. So you can have 3 types of blocks: size 3, size 2, and size 1, all the way up to 12. So basically, you can have as many blocks as you like, as long as their total height does not exceed 12. And in between the robotic arm and the obstacles, and the blocks, you have obstacles. So the obstacles are bars of varying heights as well. So the maximum kind of bar is 7, maximum kind of, and you can have a bar of 6 all the way up to 1. So you can have a very small bar that is just 1. You can have a bar of 5, and so on. Now let me just go ahead and get rid of all of these bars, because I'm not, the bars are actually there's something before the bars which I forgot to mention. So let's just leave these two spaces blank, and the bars actually start from here. So you can have a bar of size 7, a bar of size 6, a bar of size 2, and so on and so forth, up to a maximum of 6 bars. So that's 6 as well. 1, 2, 3, 4. So basically, you'll have a fifth and a sixth one. This is not to scale. You actually have a bit 6 bars total, maximum of size 7. And these spaces are where you need to stack the blocks of size 1 and size 2, and size 3 you stack it on top of the bars. So to give you an example, as the robotic arm extends and picks up this block, so it picks up this block of size 3, it's gonna put it onto the furthest bar that doesn't already have a block on it. So in this case, it put it onto bar number 7. Then it's gonna pick up a block of size number 1, and it has to bring it all the way back to the position of where we stack blocks of size 1. Then afterwards, it'll pick up the block of size 2. It'll bring it all the way back to where we stack the blocks of size 2. It'll pick up the next block of size 3, and its goal is to bring it all the way to the furthest bar that doesn't already have a block. 7 already has a block, so it'll bring it to 6 and I'll put it there. So what can the robot do? The robot can go up, it can extend, it can drop, so it can pick up. So pick up which means lock onto the block. Then it can rise, it can retract, and it can lower. So these are the basic movements of the robot. So the challenge here is to solve this problem so that the robot picks up the blocks and puts them in the right destination. So the most obvious way to do this would be to lift the robot arm all the way up to the maximum size, extend it to the maximum size, take the block and then bring it to its destination, lower it, again lift it up to the maximum height, go back to the blocks, pick up a block, again lift up to the maximum height, and so on and so forth until there are no more blocks left in the stack. Now, this is not very, while this might work, it's not very efficient, because suppose you are picking a block of size 1, you don't need to lift it up all the way to size 13 in order to pass all of the obstacles. All you need to do is, in this case, if this was our block number 1 as first, so let's just block number 1, all you need to do is you need to lift it up to height 8 so that it'll pass just 1 over size 7. So the challenge for bonus marks here is to design this program so that it will make the least amount of moves possible in order to complete the task. So let us actually get the program and get the visualization so you can see for yourself how it works. So this is my GitHub account, and I forked this repository from this guy called HRSHT1. Thank you for that. Let's go ahead and clone this into our folder. Git clone. Now we have it there. Let's cd into the folder and robotic arm spell today. And let's go ahead and close this and open it in Visual Studio Code. There we are. So we have a bunch of .class files which are provided by the professors, and they're mostly serve as the graphical user interface for the robot. And this is the file that we have to edit in order to make the robot run. So let's go ahead and compile this and run it just to see how to visualize how it works. So we'll compile all of the Java files and then we'll run it. So to run it, we have to run the Robotic class. So Java robot, and here we are. All of the blocks and the bars are default. So basically, as you can see, it picks up the blocks of size 3 and it brings them up and it puts them on bars, one next to the other. Now, in order to provide it with different kinds of sizes of blocks and bars, we need to provide it as parameters. So for example, we go 1, 2, 3, 4, 5, 6, and these are the sizes of the bars. And the next one is the size of the blocks. So 3, 2, 1, 3, 3. And then we go ahead and run it. And you see how it's different now. So we're gonna go ahead and go and do it. So it brings up the blocks of size 1 to number 1, size 2 to number 2 as it should, and size 3 is gonna put, oops, a hidden obstacle. So you see the program is not perfect, but we're gonna actually do it from scratch. So we're going to delete all of this, and we're gonna start from scratch to see exactly how it works. So we'll leave the comments just to see what the robot actually does, and we'll delete everything between these two curly braces. So let's get rid of all of that, and we can get to work. All right, so let's start with the simplest approach. So let's run this program just to give the visual of the grid. Here we go. And the simplest approach would be to just lift the height of the column all the way to the highest possible value, and then extend it all the way to the last possible value, pick up the block and put it where it needs to put it, and come back down, lift it up, raise to the highest possible value, thereby ensuring that it's not going to hit any obstacles on the way, and put it, and so on and so forth until it is done. So this is going to be our first iteration of the program. And on the next iteration, we're going to incorporate other size blocks and other size bars. And on the next iteration, we're going to make sure that it's every time it's doing the least amount of moves possible. So in order to do this, first we need to lift the robot arm up all the way to the maximum height, which I believe is 14. So in order to do this, let's define some variables first. So we need to define some variables such as the height, which is gonna be in its initial state of 2 because it starts at 2. So that's our initial state. Let's define width, which is gonna be at 1 as its initial state. And we'll define the actual arm that's gonna come down and up. So in the beginning, the arm is always equals to the height. So it should be int L. What should we call it? Let's call it job bar. the drop bar is gonna be equal to the height to begin with. So now we need to find out what how far we need to actually what our block size is. We need to find our block size in order to be able to go ahead and lift it all the way up to the block size and then know where it's at, so as we can then pick it up and then lower it a sufficient amount. The block size is basically this. So in our case it's 12. It can be any amount, but in this case it's 12. So as you can see, we have an array of integers here provided as a parameter to this function, and each element in this array is the size of each block. So what we can do is we can basically run a loop through this array. So for int I equal to 0, while I is less than the length of the block heights, dot length, and then I plus plus. And as we run this block, we're just gonna go ahead and we're gonna add. So basically, we're gonna have a variable called all blocks height, and that's initially gonna be equal to 0. And as we run this loop, we're gonna add each element of this array onto this variable, and then we'll have all, and that will give us the total. So what we're gonna do is we're gonna say all blocks height plus equals to and block heights, not block all block heights, just the array block heights, and at the index of I. So what this is gonna do is gonna actually give us all of the total size of the block stack, and we're gonna subtract from it each time we pick up the block. So now we have this variable. What we can do is we can lift up our arm, so our column, all the way to the maximum height. So while the height is actually equal to h is less than 14, remember initially it was 2, so while it's less than 14, and it's gonna be 13 because I think 14 is a little bit too much, yeah, it goes outside of our visual scope. H is less than 13. What we need to do here is we need to r.up, and I'm gonna lift the robot up, and then we're gonna increment the h by 1 each time it's gonna lift it up. So it's gonna lift it up all the way to the highest point. Once we are at the highest point, oh yeah, by the way, the drop bar is also needs to be incremented because it rises together with the column in this case. Then afterwards, we need to extend the bar, right? So what we're gonna do is we're gonna say while w is less than 10, because 10 is the highest value, on the far side of the grid for the width. So while width is less than 10, we are going to go r.extend, and of course we're gonna increment w as we do it. So now that we've extended all the way to the source to where the blocks are, we're going to lower it. So we need to we need to lower the arm in order to pick up the block if we need to lower it. So while the drop bar is in this case it's greater because it's up, and we need to go and make sure it lowers down. So while drop bar is greater than block heights, so all blocks heights, that's what we needed it for. What we're gonna do here is we are going to lower the drop bar. So r dot lower, and of course d is gonna be d minus minus, because we're gonna decrement d as we're lowering the drop bar. So once it's lowered all the way to where the block is, now we can safely pick it up. So r.pick is the pickup command. So now let's compile and run this and see if we haven't made any mistakes along the way and that it actually works before continuing on forward. So it's gonna, okay, obstacle found, because it's trying to lower it even though it doesn't need to. The problem is, of course, with this particular place right here, line 48. So while d is greater than all blocks height, and d in our case was so all blocks height was 12 and d was 13. So D doesn't have to be the same as the all of the blocks height, because that way it would be here. It actually needs to be one up. So what we can do is, while all block heights, so while D is greater than all block heights plus 1, because D needs to be one level above of the block in order to pick it up, not at the same level as the block. So let's compile it and run it again. And now we're gonna pick up the block. You see it locked onto the block, it picked it up. So the next thing we can do is we can take the block and put it onto where it needs to go, which is the first bar down. So the first bar down is always going to be at the position 3, and then the next bar is going to be position 4, the next bar is going to be position 5, and so on and so forth. So what we can do is we can define another variable, and we're going to say target for block 3. So for target block 3, and we're going to say it's 3 initially, because that's where the first block goes. And so after we pick it up, we are going to raise the bar first, if it needs to be raised, the drop bar. So while D is greater than, so let's go, while the drop bar is actually less than height, because we want to lift it all the way to H as before. So r.raise. So, and then of course D is gonna be incremented afterwards, and afterwards r dot contract, because we're gonna go all the way to position number 3 in order to draw the block. Let's go r dot contract plus institute handler. So while W is less than, what was it, 3? So W is less than 3, we're gonna go r dot contract, and of course W minus minus, so we can decrement the value of the W, and then we are going to lower the block to where it needs to be lowered. So in this case, it needs to be lowered onto the bar number 7, onto the bar of size 7, but the block is also of size 3, so we need to lower it all the way to 7 plus 3, so it needs to be 10, because the actual arm of the robot needs to be at the height 10 in order to properly lower the bar, which lower the block onto the bar, which is 7 plus 3 of total height. So while D is less than 7 plus 3, as discussed, what we're gonna do is r dot lower the arm, and D minus minus, and afterwards, while it's lowered sufficiently down, what we're gonna do is we're gonna do r dot drop, and that's gonna be our first block that is dropped. Now let's compile it and run it and see if we've made any mistakes. Let's see if it actually works. So it's gonna pick up the block size 3 can be dropped only on columns 3 to 8 only, right? So it's trying to drop it even before it's done anything else. So I pick it up, then while D is less than height, and in this case D is not, so you shouldn't raise anything at all. So while W is less than 3, is W less than 3 in our case? W in our case should be 10. Of course we have indeed incremented it. So it's trying to drop it before actually doing anything else. And let's debug it together. So basically I'm thinking the problem should be here, while W is less than 3, then what we're gonna do is we're gonna contract. So let's go ahead and print out W. Now let's print line. We print out W like this, and then see what the value of W actually is, and why it's not contracting as it should. So now we picked it up, it doesn't try to, so it doesn't even come this way. So let's kind of cut it and paste it over here, which means it doesn't enter this loop. So W, oh right, I'm actually seeing it now. I'm sure you saw it even before me. I'm just wondering, when is this guy gonna realize it? Basically, W is obviously greater than 3. It's not less than 3, because W was 10, and we need to go back to 3. So W was, of course, in this case, greater than 3. So the only way it's gonna enter the loop if it's basically I've messed up the comparison operand. So let's compile it and run it again. And let's see, now it's gonna recheck properly, and of course it's gonna try to drop it again for some reason before lowering it. So let's see why that is. Now the problem is of course here. So while d is less than 7 plus 3, which is 10, d should be equal to 13 by my estimates, and it's trying to drop it. So in this case d should be while d is greater, like I did the same mistake I did with the w. So while d is greater than 7 plus 3 because it's higher, then we're gonna lower it. Did I also make a mistake with actually raising it beforehand? Let us see. So while d is greater, it's lowering, and while d is less than height, then we raise it. Yeah, raise it. Yeah, I didn't make a mistake over there, just here. So let's compile it and run it again. And this way, I believe it is actually gonna work. Now it's trying to lower it further than it needs to, because I believe it's trying to lower it one more, because the height is actually over there. So let's instead of lowering it all the way to 7 plus 3, because remember how d was actually supposed to be plus 1, so 7, it should be 7 plus 3. Let's go d 7 plus just 2. So it should, no, actually 7 plus 4, because you need to include the d plus 1 as well. But to make it more comprehensible, because I believe that this is becoming too much of a spaghetti code, we're just gonna make a d plus 1, because the there's always gonna be another level above over the drop bar. So let's run, let's compile this, and let us run this again. And this way it's actually gonna drop it, and it lowered it too far for our liking. So let us debug this one. So d is equal to 2 in our case, and it's trying to keep lowering it until d, so while d is greater than what we assume the height should be, which is 7 plus 3, 7 plus the block of 3, it keeps on low. So let's debug it. Let's go ahead and let's print out what d is, what the drop bar is. System.out.print line, and we're gonna say print out d because we're curious as to what it actually is. And let's quickly compile the code, and of course we forgot the semicolon. That's not a problem. Let's compile the code. That's not compiled. Let's compile the code and run the code, and this should give us a better idea what's actually happening. So in our case, d was 13 because it was equal to the height, then lowers down, so it lowers to 12, it lowers to 11, and we're actually trying to get it to lower to 10, and that is a bit too far. So while d is greater than 10, even though I said d plus 1, so of course it was initially all the way to the height. So actually d should be height minus 1. It shouldn't be height, because the height is here and the drop bar is always neck down over to that. So the initial d should be height minus 1. And let's see if that actually clears things up. Let's compile it and run the code and see. D cannot be less than 0 because it's trying to raise it again, because of course in our case over here what we are doing is somewhere I said if d is less than height, then we're gonna pick it up. So here if d is less than height, so now in this case we want if d plus 1 is less than height, and if d plus 1 is not or is d minus 1, yeah, if d I think if d is less than height minus 1, yeah, this should be more comprehensible. So let's compile it and run it, and let us see how, yeah, this way it actually worked. So it still tries to lower it too far, but in this case I believe what the problem is this one, So if d is greater than 7 plus 3, which basically I believe should give us a great result. So now we dropped it and we don't have a problem anymore. So now if d is greater than 10, which was 7 plus 3, and d was indeed 11, and we didn't go to 10 anymore because it's not greater than or equal to, it's just greater than, it dropped the block. So this is the first iteration. Basically, picks up the block and it drops the block, and then after dropping the block, what we need to do is we need to make sure we subtract the value of that block from the all blocks height, because the next one is going to be lower. So what we're going to do is after dropping it, we're going to say all blocks height is minus equal to all blocks height, so minus equal to 3. So basically it's going to be equal to all blocks height minus 3. Let's just is equal to all blocks height minus 3. And after this, we're going to go again, and we're going to pick up the next block in line, and we're going to do the same thing until there are no more blocks on the stack. All right, so now let's find out what our current block size is actually is. So as we pick it up, we'll find out what it is instead of just assuming that it's 3 as we've done thus far. So to do this, we'll just have to iterate through the block heights array and get what we're currently picking up. So instead of having this while loop here, I'm thinking we're gonna have a for loop instead, and this for loop, we're gonna initialize I to be the length of the block heights array, and the condition will be while I is greater than 0, because the reason we do this the other way in the descending order is because the block that we're picking up is the one on the top, and if it's the one on the top, that means it is the last element of the array. So we're gonna do it in the descending order like this, and then of course I minus minus. And just to make sure this will actually work, let's quickly compile and run this program to make sure it does the same thing. You can speed it up. Yeah, it's exactly the same. So now that we have the access to the block heights and each specific element of the I index in the array, we could say current block will be equal to block heights at the index I. At the index I minus 1 actually, because in this case, if if the length of since the index starts at 0, so if I is 9, then of course we can have an element at block heights of index 9, because it's going to be out of range. The maximum is 8, because if it's 9, it goes 0 to 8. Yes, so it's going to be I minus 1, and then while we are doing this, we're gonna for the first two parts, it's gonna be the same. We're gonna lift it up to the maximum capacity, regardless of which block it is. Then we're gonna extend it to the maximum capacity, regardless of which block it is. Then we're gonna lower it to the to our all blocks height to pick it up, regardless of which block it is, because this is our height of the block. We're gonna pick it up, and then afterwards, at this point we're still assuming they're all blocks of size 3. So instead of hard coding it this way, what we can instead do is, let's get rid of the system. So what we can instead do here is say that if, so let's not assume that they're all of size 3. So once we picked it up, we'll say if, and we say current block, the variable that we named before, and if that is equal to 3, that is if the block is of size 3, then we are going to do all of this. So we still, actually let's cut this and paste it after, because we still raise the block to its maximum height regardless of which block it is. So we do that, and then afterwards we check. So if it's indeed of size 3, then what we're gonna do is we're going to put these two things inside of this while loop, or that's if inside of the if statement. So if the current block is equal to 3, then we're going to take it to where the block of size 3 needs to go, and we're going to put it down onto that bar. And as the next iteration, let's also get the size of the current bar. So the size of the current bar will be gotten in a similar manner as the size of the current block. So we'll need to iterate through bar heights as we've gotten from our parameters, and we'll need to get what the current bar is in order to get the current bars onto which we need to drop the block of size 3. So now the next thing we'll need to do is to just keep picking up the blocks until there are no more blocks left on the block stack. And the way we do this is we'll just have to put it all in a loop. So we'll say, so we have in the beginning we have the all of the blocks inside of this array called the block heights, and all we have to do is just to say while there are still some blocks in this block heights array, or rather an even easier way to do this will be while all block heights does not equal to 0, because you see at the end after we drop the block we'll subtract the size of the block from all of the block heights. So we can say while all block heights is greater than 0, which means there are still some blocks on the stack. All we need to do is just copy everything here and move it onto move it inside of this while of curly braces like this. And additionally to subtracting the number of the maximum block height from the number of the size of the current block from the maximum height of blocks, we also need to update the location of where we need to put the next block of size 3. So since we put the first one onto the first bar, the next one should be the next bar. So the first bar was 3 initially, so we'll need to say target block 3 plus plus, which means that you'll add an additional 1 each time there is a block 3 to pick up. Now let's run this, let's compile this and run and see if it picks up all of the blocks. So it picks up the first one, picks up, but the second one it can only pick up from column 10, which means that it's not lower and far enough in order to pick up the block. So we have a little bit of a problem given that it's not low and far enough. And the problem here is that it's just before the peak while it's lowering. So while d is less than all block height plus 1, was that plus 1 necessary here? I don't think so. I could recall. Let us sag the plus 1 from there and run it again. Yep, so that seems to be working now. So that, okay, hit an obstacle because I was trying to go all the way to I was trying to go back to 3 again instead of having, so this didn't make it, this didn't play an effect. Let us see why it didn't play the effect. So initially it was 3, and then when we contracted, we only say that while it's greater than 3. So what we need to do is we need to, instead of hard coding it like this, we need to actually use the variable that you've defined. And this is what I mean when I say we're just gonna iterate it to make it as efficient as possible. Initially we'll just do it the simplest way possible, which might include hard coding some values, and then afterwards we'll just iterate over and over until it becomes better. So now you see it picks up all of the blocks, it efficiently putting them where it needs to go, and so our program is finished for all of the bars of the same size and all of the blocks of the same size. So the next iteration we'll do is we'll make this program be viable for bars of different sizes and for blocks of different sizes, and then eventually we'll as for our last iteration, we'll make it so that it's the most efficient possible, which means that it never lifts any further than it needs to go, and it makes the least amount of moves. And the way we'll do that is, instead of, we'll just define all of the things that we've hard-coded as variables. For example, all of the block size are just added to each time a block is dropped, we are subtracting 3 from the value. So instead of subtracting that 3 from the value, what we'll do is we'll get the current size of the block directly from the array. and then we'll know what kind of block it is, because it might not necessarily be a block number 3. So since the only time you're actually gonna need to know what the current bar size is, besides knowing what the maximum height is in order to lift it up to avoid any obstacles, is when we actually have a block of size 3, because we need to know onto which bar to put it and the height of that bar. So we're gonna have a variable. It's gonna be an int, and let's just call it current bar. And this is only gonna be relevant when the block size is 3, and we're gonna give it a 0 initially. Actually, not the current bar. What we need here is the bar index, and the bar index is 0, because what we're gonna do is we're gonna use this index to find the element in the bar heights array. So we're gonna start at 0, which will be the first bar, and we're gonna iterate. So then we're gonna increment it, then the next bar will be 1, and so on. So initially it's gonna be 0, and then once the current block is actually equal to 3, and we lower it, and just before dropping it inside of this if statement, what we are going to do is we are going to go ahead and say that the bar index is now incremented. So bar index plus plus, meaning that we're gonna add 1 to the index, and the next one is going to be the next bar. And of course the current bar is going to be gotten from the array using this index. So instead of having it d equal to greater than 7 plus 3, so plus 3 is still going to be the case, because obviously the block size is 3, but instead of having it 7, because the bar can be any size, we're gonna say we're gonna say it's gonna be a bar of the element in the bar heights array of the at the position bar index. We've named it there before, and this should now get us our current bar. And since that's gonna be incrementing each time it's gonna be a block, it's gonna check for the next one another time. So since they're all 7, this should work. Let's just double check to make sure that we haven't broken anything by this. What have we broken? So current, we can't find a symbol of current block. So we define current block as so we need to specify that it was an int, of course. So, whoops, we haven't compiled it. Let's compile the code and then run the code and see if it still works after our little modification to the current bar. Yeah, it still works exactly the same way, meaning that it's finding the bars appropriately each time. And of course this here, this code here to increment the actual target drop location for the block number 3 should be inside of this if statement. So we can do that along with incrementing the bar index. So that should do it for blocks of size 3. And if we're gonna go ahead and pass different kinds of parameters to the bars, we're gonna see so for example, instead of having all of the bars as 7 7 7, we're gonna say 3 4 5 3 7 and 4, and then all of the blocks are gonna be 3 3 3 3. And let us see if our program still works given different size bars. Okay, no, it does not, because it actually hits an obstacle, because it doesn't raise the arm completely before going on to pick up the next block. So we'll need to fix that up. So after dropping, and then it goes back to the beginning of the loop, and then the only thing it does is actually picking up the actual arm. So it's not the drop bar. So if we're gonna make sure it does before it picks up the drop arm, the picks up the actual column, we're gonna make sure it's gonna pick up the bar as well. So we're gonna say while, and in this case d, because we call it a drop bar, while d is less than, and what are we lifting it up to, less than h minus 1. The same thing as here, you see we raise it to the maximum possible position. So while d is less than h minus 1, what we want to do is we want to raise it, and then of course increment d. Now let's compile this and run this and see if it's gonna work now. So now it's gonna raise it all the way before going to pick up the next block. Yes, so now we have no problem, and it's dropping it to the correct positions on the bars. All right, so this particular implementation is done. So the next one is just gonna be implementing it for blocks of various sizes. So you can probably guess. So we have a one condition here, one if statement saying that if current block is equal to 3, we're gonna do all of this. Then we can just add else if, and then we say current block is equal to 2. And all we have to do is just add some code here to make it viable, to make it work for blocks of size 2. And then else, and we'll just do else if to be more precise. And else if current block is equal to 1, which is the only other type of block that there is. And we'll just add some code here to make it work for block of size 1. So now we know that the target for blocks of size 1 is 1, just as for blocks of size 3 was 3. And the target for blocks of size 2 was 2, as to where we need to drop it. And what I mean by that is, so this is where we need to drop blocks of size 1, and this is where we need to drop blocks of size 2. So to implement this, we need to actually know how many blocks there are already on those locations, because when we are dropping the block, we'll have to actually know how far to lower it before letting it go. So let's define 2 other variables. We'll call this one block stack. Initially it's going to be 0 because there aren't going to be any blocks on it, and then we're going to say 2 block stack. And that's also going to be 0 since there aren't any blocks on it yet. And then when we are picking up block number 2, so what we've done before this is we've extended it, we've picked up the block, we picked it, we've raised the bar, and then we need to know how far to contract it, to retract it. So if the block was target block size 3, so we also we're gonna put it where the blocks of size 3 go. Now if the block was of size 2, what we are going to do is we're just going to retract it all the way to position number 2. We don't have to create a variable, we can just hard code this because it's always going to be number 2 for blocks of size 2. So we're going to contract it, and decrease the W. So that's going to contract it to the right position, and after this we need to know how far to lower it. So same principle as for block number 3, while D is greater than, and instead of the bar height, we actually need to know the size of the current block stacks, current stack of the blocks at the position number 2. So as we recall, we named the variable called 2 block stack. So if while D is greater than this 2 block stack plus the size of the current block, which is going to be 2 in this case, so we could have just said 2, but since we have the actual element, the actual variable, we can just say that, and we are going to lower it. So r.lower and d minus minus, and then once it's lowered to sufficiently far enough, it's going to drop. And afterwards, what we need to do is we'll need to add the size of the current block, which was 2, onto the block stacks. So 2 block stacks is equal to 2 block stacks plus the size of the current block. And once we've done that, we can actually go ahead and compile it and define some other blocks other than 3. So let's go ahead and just say 2, 2, 2, 2, 2, 3, 3. Wait, is that 12? So 2, 4, 6, 8, 10, 12. So that's 12. Yeah, let's go ahead and run this program and see if it takes it. So it takes it to the right location and it drops it fine. And then it's not picking it up properly. because it's trying to lower it further than it goes. So the problem in this case is in lower. So when it's trying to lower it, when we find the blocks, it always goes to 10. So it is not, the problem is not here. The problem is rather outside of either of the if statements. So the problem would be while these let an all block heights. And the reason this happened is because I didn't actually so I said that all block heights would be all block heights minus 3, whereas it should have been all block heights minus the size of the current block, because in our case it was 2 and not 3. So let's go ahead and compile it and run it again. And this should work. Of course, we can never know until we run and see. And that is the beauty of actually being able to run our code and see for ourselves. And once we see some errors, we can go ahead and debug it in kind. So it seems to be working. So I got all of the blocks and it had put them all in the right location. So we are pretty much done for blocks of size 2. And let's just go ahead and mix them up, see if it still works. So we're gonna go ahead with 3, 3, that's 6, and then 2, 8, 2, and 2. So that should be 12. Let's go ahead and run this and see if that still works. Let's just speed it up just to make everything go faster. And the other thing I wanted to try is, instead of going 3, 3, 2, 2, 2, let's go 2, 2, 2, 3, 3, because that would mean that it's going to pick up the blocks of size 3 first, and the obstacle should be higher for sources. They still lift it up to the maximum position, so there shouldn't be any problem regarding this. And yes, it still works for both blocks, and the program runs as expected. So let's go ahead and quickly do the same thing for blocks of size 1. So while W is greater than 1, because we need to take it to the position 1, all we need to do is we're going to contract it. So exactly the same thing. And W minus minus. And then we need to lower it all the way to where the to the total height of the stacks of the blocks at size 1, which initially is 0. So while D is the drop bar is greater than 1 block stack plus the current block, we are going to lower it. And of course, D minus minus over here. And after it's lowered, we are of course going to add that block to the current block. So so to the total size of the block stack at target 1. So 1 block stack side today, 1 block stack is going to be equal to 1 block stack for what's already there plus the current block we're taking, we're putting on it. So this currently should be a solution enough, and it should work for all of the blocks of size 1 as well. So let's go ahead and compile it. And then run the code again. And instead of having it as 3, 2, 2, so we're gonna have it 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, that's 12. So let's go ahead and run it. It's gonna take a while, so I'm gonna speed it up. And yeah, basically it worked exactly as expected. So let's give it some other types of blocks. So instead of having it, let's go 3, 2, 2, so that makes it 7, then 3, 10, and then 1 and 2. So there's only going to be 1 block of size 1. So it's going to be a whole bunch of blocks. I think I've exceeded number 12, the amount. So it's going to be 3 plus 2 is 5, 7, 10, 11. Yeah, I made it 13. So let's get rid of this 2, and instead of making it a 1 as well. There we go. Let's go ahead and speed it up. So yeah, it basically puts all the blocks in the right locations, again as expected. So this, in the case of our assignment at my university at RMIT, this would have been the minimum that you had to complete in order to pass the assignment. to just have it be able to pick up all kinds of blocks and put them on all kinds of size of bars. The next iteration will be to actually have it do so efficiently in the minimum amount of moves. So, for example, we don't need to lift it up all the way every time. We just need to lift it up sufficiently to pass the highest obstacle. So this is what we're gonna do in our next iteration of this code. We're just going to unhard code a lot of values, find the maximum height of the highest obstacle, and we're going to do it efficiently in the minimal number of moves for the bonus marks. All right, so this was the base implementation of the program. I didn't go so far as to actually implement the full extent of the challenge, which would imply to solve it in the minimum possible amount of moves, because this video I realized has gone on for a little bit too long. It's drawing onto 50 minutes now. So if you stuck with me for this long, thank you, and I hope you enjoyed this problem as much as I did. I will release a part 2 of this video in which I will actually go through the implementation of the most efficient design for this particular challenge, where we'll complete this robot to have it move all of the obstacles from one side of the grid to the other in the minimum amount of moves. In the meanwhile, I highly encourage you to go ahead and find this program in my repository or on my GitHub account. I'll leave the link down in the description, and try it out for yourself. See if you can solve it, and if you can, share it with me in the comments. See you in part 2, and as always, have a great day.